My TTL computer. Today is part 3 of our overview of revision 4. And today we're going to be looking at mostly at the assembler and our source code of our bank test program that we've been looking at. And we're going to our goal is to get a better idea of how the bank switching is really operating in this environment. Okay, so let's get going. All right, so I have my editor open, and this is our bank test program that we looked at last time. And just a quick review that we're starting out in bank 4 here. It's address 400. And we have our bank 4 message. It just loads A immediate with the ASCII characters for bank 4. And it outputs those using the out command to the screen. And then at the end, it jumps back to the monitor. Now, we see here that we have a new instruction, jump far. Now, that is a special instruction that operates in the bank environment, and that will be able to do a jump between banks. The regular jump statement still is present, but that's essentially a near jump. That will only jump within a bank, and jump far will jump any place in the address space, the 2K address space. Okay, so that's the first part of our bank. That's the origin is in bank 4. Then we have our next piece is our origin is in bank 5. And we see this does the same thing. It outputs bank 5 characters, and this, however, does not jump to the monitor. It jumps to the bank 6 message. So that jumps right to here. We have the origin statement at address 600, which is bank 6. Same thing. Puts out the bank 6 message and then jumps far back to the monitor. Okay, so that's how that works. Right? We just say go 400, it says bank 4, and then jumps back to the monitor in bank 0. If we do go 500, it says bank 5, and then it does a far jump to bank 6, and the bank 6 message just puts out bank 6 and does a far jump back to the monitor. So that's what that is. We'll take a look at the program running at the end just to see how that works again. Okay, now we're going to take a look at the assembly output from our source code, and I've already run this through the assembler. And the big change in the assembler is now this is a 2-pass assembler. At our prior revision was a single pass assembler, but this has gone to a 2-pass assembler. And the main reason for that is so that we can see the opcode that is generated for each statement in the listing file. And we can see that here. We have load A immediate with the B character, and we see here's the opcode for load A immediate, and then here is the data, the hex value for capital B, and then we have the out command, and here is the object code or the hex value for the out command, and then on for the rest. So we can see here that we have a 2-byte instruction word and 1-byte instruction words coming down through the rest of these instructions. Now we hit the jump far, and the jump far we can see is no longer a 2-byte instruction word. We're up to a 3-byte instruction word for any instruction that operates across banks. Requires a 3-byte instruction word. Now, all right, so here we are with the origin statement with address 400 means we're in bank 4. And we can see here, all of our addresses are in the 400 range, are in bank 4. Now, you remember from our prior video that the lower 4 bits of the opcode are what's driving setting the high 3 bits in the address space. So we can see that these opcodes, right? This is the opcode goes in the instruction register. All of these in bank 4 end in 4, right? And that really it doesn't only coincide with bank 4. It defines that these instructions reside in bank 4. All right, we go down to the next message, the bank 5 message here. You see org 5, right? We have the same instructions in here, but all of these now are bank 5, and we can see that in the lower nibble of the opcode is all bank 5. Same thing now with the bank 6 message. You see that all of these, the lower nibble and the opcode, are all specified bank 6. So it's not just, again, it's not just coincidental. That lower nibble in the opcode defines this as being this instruction being in bank 4. Okay, so now so this kind of all operates as usual. The fetch cycle and everything is all the same. Now, what makes this far jump different? So my TTL computer, it loads the first byte of the instruction, the first word of the instruction, and the high nibble is 6, right? That's the instruction code for far jump. The lower nibble is 4, so that says that we're in bank 4. So we're starting out in bank 4. Now the microcode, so this data that we're next looking at, the 60 and the address, this is all loaded in bank 4. So the microcode has to load the the destination opcode, the destination bank opcode, and the destination address. The microcode has to load that while it's still in bank 4 to get that data. After it has this data, it will set the program counter. It's still in bank 4. It sets the program counter to 0, right? The destination bank program counter is set to 0. And then the last thing that the microcode does is it takes the destination opcode and puts that in the instruction register. So as soon as that happens in the microcode, we are now operating in bank 6 with address 0, right? Which is all the way down here, right? We're here now after that far jump is executed. All right, so let's review that one more time. So my TTL computer is operating in bank 4. It's going through, executing all these instructions as usual. Some are 2-byte instructions, some are 1-byte instruction. So now we get down again to the jump far, which is here we're going to be doing a bank switch. So the microcode loads the opcode from bank 4, and it has 6 indicates that this is a far jump, and then the 4 again that we're still in bank 4. So while we're still in bank 4, the microcode has to load the destination opcode, and it loads the destination address, all while it's still in bank 4. Then it loads the program counter with the destination address. And the last thing the microcode does is it drops the destination opcode into the instruction register. And at this point, we now are in bank 6 at address 0, right? We're here coming out of the far jump. And then we're back. Now we're back executing as usual. We can see there's all in bank 6. Then we have the far jump here back to the monitor, and we see again, the microcode starts out in bank 6. It loads the destination opcode, which is in bank 0, and it loads the destination address. it sets the program counter to the destination address at 0. And the last thing the far jump microcode does is it puts the destination opcode into the instruction register. And again, this is the bank switch. Now we're operating at bank 0 at address 0. Okay, so that's how that works. And okay, so now let's just review and see this thing in action and running. And I already have my TTL computer up and going. We're going to start the terminal now. And first thing we need to do is load our bank program that we just reviewed, and we looked at the assembly output, and that is loaded. Okay, so now we can use our go commands, and we can go to address 400, and we see there's our bank 4 message. We can go to bank 600, and there's our bank 6 message, and we can go to address 500, and there's our bank 5 and bank 6. Okay, so we reviewed the source code, and we've got an idea that what the source code looked like for the bank program, and we introduced the jump far statement that we use to jump between banks. And we also looked at our assembly listing closely, and we saw that we have 1, 2, and 3 byte instruction words, and that 3 byte instruction words now are required for any instruction that's working across banks. And we also just reviewed the execution of this program, and we saw how we could, again, using the monitor, jump to different addresses, and we saw that bank switching in action. Okay, so now I have a little bit of a reveal, and I played a little trick on you. I said that we looked at this, and actually we've had nothing running on my TTL computer today. What we just launched was a my TTL simulator that I've developed, and all that we looked at here was actually running in the simulator. So that this is really, the simulator is really going to be a game changer for software development for my TTL computer. It's going to make the development go much easier, since I can, just quickly edit the files and assemble those and run those right in the simulator. So, and the simulator, I've only just scratched the surface today, just showing what the simulator can do. And if there's interest, I'll do another video that looks at the simulator more in detail, because it's pretty powerful and really a great tool, and is just going to be much improved from developing just using my TTL computer and the 8-bit terminal, which we are not using right now. Okay, so I hope this was helps to clear up how the bank switching is implemented and operates. And so our next video, I'll probably do a little bit of a deep dive on the simulator, because it's I said it's a game changer, and you'll see that when I show you all the things that it can do. Okay, so that's it. Thanks for watching.